We're talking about the line of best fit, the best line of best fit, or is it? So basically we're analyzing lines of best fit. And one of the things that we talked about that I'd like to look a little bit further on is what is considered a good versus bad residual plot. So forgive the random ads because this is a website. Do the residuals exhibit a clear pattern? So in a good residual plot, the residuals exhibit no clear pattern. In a bad residual plot, the residuals exhibit some type of pattern, such as a curve or a wave. This is an indication that the model we used does not provide an appropriate fit. And that makes sense. And if it doesn't make sense, then I'm going to show you some examples here in a second. Let's scroll down a little bit more. Do the residuals increase or decrease in variance in a systematic way? So what's that mean? Well, in a good residual plot, the residuals are randomly scattered about the zero. There's no systematic increase or decrease in variance. In a bad residual plot, the variance of the residuals increase or decrease in a systematic way. Again, if you're like, what does that mean? Let's just keep going. So here's an example of a good residual plot. So what does good mean? Well, the idea is that if we were on zero, if all these dots were on zero, then they would be perfectly on the line of best fit. But because this one's good, what they're trying to say is these are just like randomly off the line. Like this is 4 and 2 and 3 and 2 and 1 and 1 and 3 and 2 and 3. You get the idea. So let me scroll down the line. This drawing might move around with the graph or with the website, so don't fall in love with it just yet. Do the residuals exhibit a clear pattern? No. They're randomly scattered about the zero with no clear pattern. So that's one reason why we call it good. And then the other reason is, do they increase or decrease in a systematic way? And the answer is no. They have a fairly consistent variance, which what they mean is the distance between the residuals and zero. Like if they were all going up in a line, okay, well that would be increasing in a systematic way. If there was a curve, that would be a systematic way, right? So let's check out a bad one and where there'll be a clear pattern. I mean, it's very clear right away. Yeah, there's zero, and then here's like the pattern is, oh, it's this far away, this far away, this far away. Boop, 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 boop. You can see that there is like this curvature, right? So that is going to be a bad line of best fit. Let's scroll down again, just see kind of what they say about it. So do the residuals exhibit a clear pattern? And yes, there's clearly a curve. Do the residuals increase or decrease in a systematic way? Yes. The residuals have different values of variance at different levels of fitted values. So since we said yes, this thing stinks. Are there any other examples here? Okay, here's another bad one. Suppose we fit a model on this one. So let's see, why is this one bad? Well, there's zero. And then here's my thought, is these kind of go up and away, and these kind of go down and away. So let's scroll and see what the website has to say. Look at all these ads, it's crazy. Sorry. So do the residuals exhibit a clear pattern? No, there is no clear pattern. And then 2, do the residuals increase or decrease in a systematic way? Yes, which is what I said. The green line seems to go up, the yellow seems to go down. And since we answered yes to at least one of these questions, we consider it to be a bad residual plot. And then here's a fun Jeopardy word. In this particular example, the residuals suffer from heteroscedasticity. I'm not sure that's how you say that, but that refers to unequal variance. And if you're like, what the heck is variance? Basically think of it like varying, right? Anyway, so this hopefully explains a little bit about it. If it doesn't, then my bad. I'll do what I can to try and explain it. Just think this one's good, because there's no clear pattern, okay? And it's also good because there's no increase or decrease in a systematic way. This one's bad because there's clearly a pattern and there is a systematic increase or decrease. This one is bad because while there is no clear pattern, like a curve, there is definitely a systematic increase or decrease. In fact, it had both. Okay? Okay. Jumping into the assignment, use residuals. So basically, these are going to be the residuals to determine whether the model is a good fit for the data in the table, and then please explain. So as I'm looking at this, if you're like, I don't really know, one thing we could do is we could graph this thing. So here's our graph, and then I'm going to kind of just give it like, that's 5, that's 10, that's 5, that's 10. Okay, so negative 10, 10, 5, negative 5. Okay. So out at 4, 1, 2, 3, 4, 5, 6, 7, 8. Now, hold up. Let's do 5, 10, 15, 20. Because I'm noticing this goes out to 20. Okay? All right, so what we've got going on is at 4, negative 1, not bad. 6, negative 3, 8, negative 6, 10, negative 10, 14, negative 10, 16, negative 10, 18, negative 9, and 20, negative 9. If you were to kind of follow this, it looks kind of like a curve to me. At any rate, I feel like they are quote unquote systematically kind of decreasing and away from our line here. And so I don't think it's a line of best fit. So no, this is not a good fit because the residuals are not evenly distributed about the horizontal axis. The table shows the growth y in inches of an elk's antlers during the week. The equation models the data. Is the model a good fit? So this is the table, and this is the model, okay? So what I'm actually going to do is I'm going to plug in this info so that I can get the residuals, because that's how we're going to kind of know, oh, hey, it's a good fit or not. So when you plug in 1 right here, negative 0.7 plus 6.8, you get 6.1. Dude, that is very close to that one, right? And if we plug in 2, we get negative 1.4 plus 6.8, and that is, let's see, 5.4. 5.4. Again, we're very close. We plug in 3, that's negative 2.1 plus 6.8. That would be 4.7. So that one's on the money, and or right on it. They're both the same is what I mean. Sorry, old man phrases, I guess. Negative 2.8 plus, I'm thinking 3.9 because of that. 6.8, we would get 4. So again, very close. So you know what? I'm just going to stop there. 4 is enough for me to say, yep, the model is, I don't have the multiple choice in front of me. So yes, the model is a good fit. Not sure what the choices are, but I would think that's what it says. All right, this one says, use technology to find an equation of the line of best fit for the data, round the slope to the nearest tenth and the y-intercept to the nearest integer. Now, I'm not 100% sure how well this will show up in the video, just because I'm just not sure how it will show up. So we did this with Desmos. So you're going to go to desmos.com and then click the graphic calculator. You're going to hit the plus sign. Oops. You're going to hit the plus sign and hit a table. And then notice it already has our X and our Y. So here's what I'm going to try and do. I need to zoom out because I can't see the keyboard on my screen. There we go. I'm going to type negative 15. And I'm just going to hit enter. And I'm going to do all the X's first. Just a little bit easier for me. Oh, wow. It actually fills it in for me. That's cool. So there we go. We got our X's. Our Y's, negative 4, 2, 7, 16, 22, 30, 37, 43. Hopefully you're not confused on where I'm getting this information right there. So back over here, browse. You can either just tap right here, or you can hit the plus sign and hit expression. So I'm just going to tap right there. And now here's the tricky part. Y1. And then I hit ABC. ABC was right down in this area. And it brings up this keyboard. And I want to hit this little thing right here. Looks like a little squiggle. And then I'm going to type MX with a 1 plus B. And then I hit return just so that it kind of would go down there. If you want, you can try zooming out. Again, this is kind of funky because I'm using an app within an app. So there are all my dots. If I turn off this line, there you go. You can obviously see that it's pretty decent positive correlation. And then when I put the line in, there it is. And then now we can zoom in here and we want our slope and we want our y-intercept. And then our R value is incredibly good. We are really close to 1. So let's go back over here, and the first thing we're going to do is try and type in. Actually, the first thing we're going to do is try and move this graph out of the way so we can write our answer. And I also want to see kind of the directions, because it says identify the correlation coefficient. Oh, that's the R. Sorry, I was thinking I was reading about this. Okay, so we are finding the equation, rounding the slope to the nearest tenth. So we have y equals 1.4x plus 15.7. Nope, just kidding, because it says the y-intercept to the nearest integer. So we don't want 15.7, we want 16. So there's that one. Identify the correlation coefficient, round to the nearest thousandth. Well, we had 0.9987, so to the nearest thousandth, tenth, hundredth, thousandth. So we're going to have 0.999. That's the answer. All right. Interpret the correlation coefficient. X and Y have a, I'm not sure what the blanks or the drop down is, but I would guess it's a strong positive. I'll go look up the answers. Guess what? That's exactly what it was. And so now we're going to do this again. Instead of showing you how to do it, if you need to see how it's done, just rewind the video and watch that part. Instead, I'm just going to jump to the answer basically and interpreting it with you and for you. Okay, so there's the graph of this table. And first thing I'm going to do is actually turn my line off so you can kind of check out. That's what the dots look like. Let's be honest, it looks not super great as far as like, oh, it's definitely positive or negative. Then when I turn the line on, okay, so sure, it's negative. But now let's look at our information here. The slope right there, the y-intercept right there, the R value, negative 0.4. That, my friends, is not a real strong correlation. So we're going to go up here, do the same thing we just did for the last one. So this is y equals negative 1 point, let's see, round to the nearest tenth, negative 1.1x plus nearest integer is going to be 12. The correlation coefficient round to the nearest thousandth, tenth, hundredth, thousandth, that's just going to be negative 0.406. The x and y have a weak negative correlation. If you're not sure why it's weak negative, well, it's the weak because r is not really close to 1 or negative 1, and then it is literally a negative number because of the negative slope. So in this next one, it's kind of funky because if you were to really try and look at the numbers, like the graph, I mean, think about it. The information goes up to 2092. So, I mean, if you were to try and check out that graph, that line, I mean, it looks pretty like oh, okay, they're all going straight up and down. And now when we turn the line back on, I mean, it is quite a tall slope, right? The slope is let's zoom in, 379.64. I mean, it's rising 379 and some change for every one it goes over, right? There's the y-intercept. There's our r value, so it's pretty accurate, right? So we're kind of doing the same thing we've been doing. Use technology to find the equation of best fit. Round all values to the nearest integer. So we're going to have 380x minus 557. Now this next part, I would think you would find a little annoying, except let me show you kind of how I'm going to think through this. So I'm going to come back over to my technology, and what I'm going to do is I'm going to hit this little wrench right here to mess with the settings, and I'm going to mess with the settings to make it look like this. Okay, so let's do that. So first thing I'm going to do is I'm going to change my x to, let's see, -4. Because if you look at these, see how they're just going like 2, 4, 6, 8, and then that's like -2. So I'm gonna go -4 to 8. And I'm not gonna mess with the step. And on my y value, I'm gonna go -100 all the way to 1900. 1900, there we go. And I'm going to tap out of that. And it's not exactly perfect, mainly because of the screen being, it's like, hey, listen, I'm pretty wide screen. So even though you wanted -2 to 8, actually, let me just double check that I didn't accidentally do -4. I did -4. Okay, -2 then. Let's see if it likes it a lot better. Okay, that is better. So now you can kind of compare it, this one to these, and you can tell that the line is going in between some of the points. There's 2 on top here, 3 on bottom, 1 on top. So it's gonna look like this one right here. And if you're wondering, why the heck would they do this to us? Well, it's kind of like I mentioned back way up there on the last one, that this, if you were to look at it the way we had it, it was like pretty much straight up. But this is clearly, as we interpret it a little bit differently, we go, oh, look, it is definitely this one. And then once the correlation coefficient rounded to the nearest thousandth, so it's exactly 0.989, so we're just going to do 0.989. And let's see, strong positive correlation because of that line being like that. Okay, so I've put all my information in for this one, number 6, in case I kind of blipped over this too quickly for you. And you might be thinking, well, hang on, AJ, that's my name. Hang on, Mystery Math. What's going on? I can't see any of my points. The home button, this little guy right here, well, now it's not there because I've hit home. There's a little picture of a home. Click home, it'll take you back home. That's your friend when you get lost in Desmos. So one thing I like about this one is that our x values were not just 1, 2, 3, 4, 5 or 5, 10, 15, 20. It's kind of random, as maybe you got information from random people and then you put in the information. So anyway, it looks like this, and here is our information here. Use technology to find the blah blah blah, and we've done that. So this answer right here is, I'm going to write it above, I'm going to write it right here, is y equals -0.08x plus 3.8. And if you're wondering, why is that one 3.8? The other ones have been like a whole number. They were really integers, whatever. This one actually says to round them to the nearest 10th, and I know that's a little annoying because that's been inconsistent. Well, guess what? That's how directions can be sometimes. And this next one says round it to the nearest thousandth, what's going to be annoying about that is, look, there's our R value, negative 0.96. You're going to put negative 0.960 because that's the nearest thousandth place, okay? And then 0.96, that's pretty strong, and it's negative, so it's going to be a strong negative correlation. Now it says interpret the slope and the y-intercept. Well, let's see. So the slope says that the more TV you watch, the lower your grade is going to be. So more TV hours, lower GPA. And then it says approximate the GPA of a student who watches 14 hours of television. So we could kind of zoom in here and we would say, there's 14, so about right there. And if we were to look, so let's see, following over here, that's 2.7. And if you're like, well, hang on, 2.7, that maybe. So that's my maybe. And then what I'm gonna do is I'm actually gonna plug it into this. And so when you do 14 hours times negative 0.08, you get negative 1.12, and 3.8 minus 1.12 is, let's see, so that's 2.68. So my guess was 2.7. Cool. The answer is 2.68 based off of that equation right there. Predict the GPA of a student who watches 1 hour of television each week. And so we could do the same thing. Basically, it's going to be 3.8 minus 0.08, which would be 3.72. So 3.72. Describe and correct the error in interpreting the technology display. So here's their conclusion, and that's the error. So the data has a strong positive correlation. Well, here is where we would find that information out, and oops, it's a strong negative correlation because that is a strong negative number, meaning it is very close to -1. Tell whether a correlation is likely between the amount of time spent talking on a cell phone and the remaining battery life. You're on your phone. The longer you are, what happens to your battery? I think we all know. It goes down. So there is a negative correlation, right? And there is a causal relationship, because as you cause the time to go up, your battery goes down. How about between the height of a building and the number of steps inside? Okay, so height and let's see, steps. So as the height goes up, I would think that the number of steps go up, right? Because if you're thinking, what about an elevator? Well, there has to be like a fire exit. So I'm definitely going, we got a positive relationship, and there is a causal relationship, because like I said, I think it goes up like that, and I think if you have a higher building, you're going to have more steps. Tell whether number of hats you own and the size of your head. I don't think there's any correlation here, because if you have a really tiny head, does that mean you own fewer hats? And if you have a really big head, you own a lot of hats? So I'm going to go with there's no correlation. There is no causal relationship, because the number of hats you own doesn't matter to the size of your head. That's a fun one. Now we have the weight of a dog and the length of its tail. So I have to tell you that I'm actually pausing and redoing part of this video because I definitely said no way. But funny enough, the book says that this is possibly positive, And I'm laughing a little bit because, I mean, I've just seen a handful of dogs, and it just seems like all their tails are random, you know. But, I mean, if you think about it, if you have a really big dog, I mean, the chances are it's going to have a bigger tail than... So here, let's go with weight and tail length. I mean, I guess it kind of makes sense that if you have a dog that weighs a bunch because it's huge, then it's going to probably have a longer tail. I didn't even draw a long tail. It's probably possible that it's going to have a longer tail than this dog, right? I mean, I guess that makes sense. So it's possibly positive. But there's not a causal relationship because the weight of the dog doesn't really determine the length of its tail. So does not determine the length of its tail. Anyway, so next we are match each graph with its correlation coefficient. Let's see, R is 0. That one should be easy because it's like, listen, you are way off in every way, shape, or form. I'm going to go with that one's R0. R equals positive 9.8. This one's 9.8 here because it's very on things. Let's see, so hang on. Colors. Negative 9.7, I'm thinking this one because, or sorry, 0.97, because it's pretty on that graph and it's going down and to the right. And then last but not least, positive 0.69, so that's positive. It's a little scattered though, so I could see how they're saying that that is not a really great line of best fit. And I think we're done. So let me know what questions you got. See ya.